Morning, y'all. I had a good weekend. Good weekend. Birthdays and the like. Let's see. I'm gonna hand back your quiz at the end of class. Y'all did pretty well as a class in general. So if you feel like you didn't do very well, come see me. I'll give you some pointers. But my big pointer to you is just to read the book. And in general, reading the book will help you in this class. Students in the past who have made A's in this class say that's primarily what they do. They read the book and they come to class. So your test will come largely from the book. Your tests will come from the book. Although your test will also come from the notes. But largely I follow the book pretty closely. So if you're reading along in the book, you'll hear a lot of that stuff again in class. All right. Also, we have a few weeks till our first exam, so it's nothing pressing. But as long as you're sort of keeping up with reading the book and what have you, you should be pretty good. And then you're reviewing your notes every couple of days. All right. And let's see, one other thing. Oh, we'll probably have another quiz next week. So another reading quiz. Let's see, today's Tuesday. I don't know, I'll let y'all know this Thursday. It'll be Tuesday or Thursday next week, but it'll be on chapter 2. Alright? The quiz okay? Like, okay about it? Yeah. I'll put your grades up on Moodle and I'm going to hand them back today so you can keep them. Any questions? No? Alright, well let's do some more of the questions, the clicker questions that we did last time. We started these, but we didn't finish them. Just about Newton's laws. Did this, that. All right, let's try this one. What can you say about the force of gravity acting on a stone and a feather? So if I have a stone and a feather, what can you say about the force of gravity acting on those? And you might know, by the way, that the acceleration due to gravity is the same for everything. Are you all aware of this from high school, probably physical science? So objects that are falling within the Earth's gravitational field, they all fall at the same rate, about 10 meters per second squared. So then how does the force of gravity then acting on a stone and feather differ? Or is it different? I mean, you can ask your neighbor. I encourage you to ask your neighbor what they're putting. Hopefully everybody gets the right answer. All right, I'll stop at, say, 118. 118. I think that's about everybody. Let's see, most of you put D. All right, so let's go back to our Newton's second law. B is the right answer, by the way, here. Our Newton's second law says that the force is equal to our mass times acceleration. And our acceleration for both of these is the same, right? For the stone, it sees an acceleration of 10 meters per second squared, and for the feather, it sees an acceleration of 10 meters per second squared. However, they have different masses. Presumably, the stone is heavier, right? Stones are typically heavier. So it has a bigger mass, and that means that the stone will have the bigger force due to gravity. It has the bigger weight, right? However, the acceleration is the same. You can wow your friends with this. Let me fish something out of the garbage right quick. So if I take a heavy object and a light object, like this sheet of paper and this pen, which is a little bit heavier than the paper, and I drop them, which do you think will hit the ground first? The marker will, right? We'll try it. This should be pretty good. Yeah, by a long shot, right? The marker hits first. But I thought that we just said that the acceleration due to gravity is the same for both the marker and the paper, regardless of the mass. Did I just say that? I think I said that. So what's the deal then? Why does this one fall at a slower rate than this one? The air resistance, right. So if I can get rid of the air resistance somehow, then they will fall at the same rate. So an easy way to get rid of the air resistance is just reduce the area, right? And if I reduce the area, even though this one has a much smaller mass, then they should fall at the same rate, which they do really closely. So you can do that with your friends. They'll always sort of throw them off. And by the way, if I wanted to draw the free body diagram for that piece of paper, this is my piece of paper. I have a force weight, or the force due to gravity, going downward, and then going upward. As Janelle said, I have the force due to the air resistance going upward. And that causes it to accelerate at a slower rate than the pin, which doesn't have the air resistance, or has very little in comparison to the paper. Remember, this is our free body diagram where we draw all the forces as they are acting on the object. All right, what can you say about the acceleration of gravity acting on the stone and the feather? I'm going to stop at 25. 25. We just said this. It should be an easy one for you. 25. Excellent. D is the right answer. All objects always feel that same acceleration due to gravity, or the same effect of gravity, rather. All right, a block of mass m rests on the floor of an elevator that is moving upward at constant speed. What is the relationship between the force due to gravity and the normal force on the block? Right. So I have this elevator, and it's not accelerating. It's moving at a constant speed. And I want to know what is the relationship between the weight and the normal force. Is the normal force bigger than the weight? Is the normal force equal to the weight? Is the normal force less than the weight? Or is the normal force 0? Or does it depend on the size of the elevator? You might not know this right off, so I'm going to show you when we're done, but I want to see if you know what the answer is. Well, we'll stop in about 10 seconds, say at 120. Just guess if you don't know. If you're not sure, just guess. Okay, yeah, we're sort of all over the board here. Actually, the right answer is B. Well, let me show you why. So if I draw my force diagram, my free body diagram, I have how many forces acting on this block? How many are there? Well, what's one of the forces? The what? The gravitational force. Thank you. So the weight is acting down. I'll call that Fg. And then there's another force. Because of Newton's third law, I know there has to be an equal but opposite force. What is that force? Well, what's the other force? It's in the problem, right? What is it? The normal force, right? So the equal but opposite force is the normal force. That's Fn. And I know from Newton's second law that the sum of the forces is equal to ma. Remember, that's that net force. And so if I sum up those forces, that's Fn minus Fg. That's the vector sum. Up is positive, down is negative, right is positive, left is negative. That's equal to our mass times acceleration. Now the question I want to ask myself is, what is the acceleration? If I'm moving upward at a constant speed, what is my acceleration? So 0. Thank you. Oh well. Noah. Yeah, so my acceleration is equal to 0. And so if my acceleration
is equal to 0, Fn minus Fg equals 0. So that means Fn has to equal Fg, which was the answer. B is the right answer. Okay, now that's going to be different if the object is accelerating up or accelerating down. By the way, the normal force you can measure pretty easily. A scale that measures your weight, that measures your normal force. So it's just simply measuring the normal force. So you can get in an elevator or whatever, especially in a big building. In this building, it doesn't really work because the elevator doesn't go quickly enough. But in a big building, you can stand on a scale in the elevator, and you can measure what is the normal force and how it changes. It's actually kind of cool. So like if you ever go, I don't know, to Homer or whatever, where they have big buildings, you can bring your little bathroom scale with you and put it in the elevator. And then people will think they're really cool. All right, so let's think about what happens if the acceleration is not 0. So here we have a situation where it's accelerating upward. All right, so what we have is still true. That is that the weight, Fg, I think I was calling it, minus Fn is equal to ma. And before, the acceleration was 0, but here the acceleration is not 0. So if this is accelerating upward, what is the relationship between the normal force and the weight, mg? Is the normal force bigger, equal, smaller than the weight? Is it 0? Or is it the size of the elevator? Now, let me tell you right now, y'all are split sort of between A and C. So ask your neighbor what they put. They're pretty evenly split. Either A or C is the right answer. Okay, let me ask you a question here. So, what is the value of this acceleration? What is the sign? Is it positive or negative? Positive. So this value minus this value, oh, I'm sorry, I have that backwards. Let me fix that. Sorry. So let me draw my free body diagram. This is my normal force. This is my weight. So my normal force minus my weight is equal to ma. You see how I had it backwards? I have my normal force negative when everything is positive. All right, so if this value is positive, what I'm asking is how are these two related? One's bigger than the other, and which is it? All right, just gonna go a few more seconds, say 228. Y'all are still split pretty evenly, like half and half. 228. All right, so the answer here is A, that my normal force is bigger. Because if I have a positive value over here, then this value must be bigger than this value, right? Like if this is 8 and this is 5, then this is going to be 3. So my normal force is bigger when I'm zooming up. You can think about this if you've ever been in a rocket ship. Have you ever been in a rocket ship shooting out into space? You have? No, I haven't either. But you can imagine that as you're being pushed up into space, that normal force gets really big, right? Because that chair is pushing onto the back of you as you're accelerating really quickly. The same happens in an elevator. That it's like you're being rocketed out into space. It's like the floor is pushing up on you. And that means that your normal force then is going to be bigger than our weight. Okay? So I think I have another question about this. So if you take your bathroom scale into the the elevator, thank you, Emily,
and it starts going up, and normally, I don't know, you're like 180 or whatever, and then it starts going up, and then it's going to reach slightly more than that, maybe 182, 183, at least while the elevator is accelerating. Now let's go back to that one. What happens then if instead of accelerating upward, the elevator is accelerating downward? Which of these is true? Is the normal force greater, equal, less than 0, or does it depend on the size of the elevator? So now instead of accelerating upward, it's accelerating downward. That means that this acceleration, instead of being positive, is going to be what? Negative, because down is negative. So now I have a negative value on the right-hand side of this. So the normal force is bigger, equal, less, or 0 in comparison to the weight. I'm going to stop at 105, y'all. 105. I'll go to 110. I think we have 37. That's about everybody. 110. Okay, very good. So the normal force here is less than. And the extreme case of this is what? Where our normal force goes to 0. If you're just falling, like say you're in, I don't know, a rocket ship, and now instead of going up, it starts falling down towards the Earth, then you're going to have 0 normal force. And we call that what? When there is no normal force. We call it what? Free fall? Well, we call it free fall, but that's weightlessness, basically. So whenever you're in free fall, it has the effect of being weightless. So when people go up to the space station, it's not that they're weightless, it's not that there's no force of gravity on them, it's that they're constantly in free fall. So it's like they're falling around the planet Earth. And because of that, their normal force is 0. There is no normal force on them, so they're weightless. They feel weightless. All right, you tie a rope to a tree, and you pull on the rope with a force of 100 newtons. What is the tension in the rope? We haven't talked much about tension, actually. I don't think, did we cover tension at all? No, I don't think we did. I'll give the answer to this one. The answer here is C, it's 100 newtons. Whenever you have an object that is under tension, that is, you're applying a force to it, if that object doesn't stretch, that's rigid or whatever, then that force is felt all the way throughout the object, the rope or the muscle or whatever it is that you're talking about. So in this case, if I have a rope and I'm pulling on it with 100 newtons, then the tension in the rope all throughout the rope is 100 newtons. So C is the right answer. Hey, good job. Very good. I'm very proud of you. I actually was quite glad for the quiz. It felt like y'all had prepared. Y'all had prepared? Read the chapter and stuff? Because you did quite well on it. All right, 2 tug-of-war opponents each pull with a force of 100 newtons on opposite ends of a rope. What is the tension in the rope? So I have one guy pulling over here with 100 newtons and another guy pulling over there with 100 newtons. They're pulling on opposite ends of the rope. The rope isn't moving. It's like they're in a stalemate. So what then is the tension in the rope? I'm going to draw a little picture.
Everybody's sort of falling on either 0, 100, or 200. All of which are good answers, right? So what you want to ask yourself, the question is how is this different from the previous question? How is this different where I have a guy pulling on a rope that's attached to a tree? How is this different from that scenario? Or is it different? So ask yourself that question. Is this scenario different from tying the rope to a tree and pulling on it with 100 newtons? I'm going to stop at 150. 150. So just a few more seconds. Just decide on your answer. Okay, yeah, we're still sort of all over the board, but the answer is C here. Because the fact is, this isn't different. Like, even when I had a tree over here, if I had a tree right here instead of a guy, or maybe it was a guy that looked like a tree, or a tree that looked like a guy, I don't know. But if I had a tree, I would have the exact same scenario. I would be pulling on one end with 100 newtons, and the tree would also be pulling on the other end with 100 newtons. Right, so in this scenario, I have the same tension all throughout the rope, which is going to be 100 newtons. You and a friend can each pull with a force of 20 newtons. If you want to rip a rope in half, then what's the best way? You pull on opposite ends of the rope, you tie the rope to a tree and pull on from the same end. A and B are equivalent. Both of those are the same. Or you get a big dog bite rope. All right, I'm going to stop at 110. 110. Actually, no, I want to talk about this for a second. So we've already said that if I have these guys pulling on the rope, what is the force in the rope? What's the tension in the rope? If one guy's pulling 20 newtons, the other guy's pulling 20 newtons, what's the tension in the rope? 20 newtons. 20 newtons. All right, so now in scenario B, what is the tension in the rope? I have two guys down here pulling on the same end of the rope, each with 20 newtons in the same direction. So what then will be the tension in the rope? 40 newtons. Then I'll have 40 newtons because I have two forces pulling in the same direction on the rope. So I'm going to have 40 newtons. So C is not the correct answer. These are not equivalent because in one case I get 20 newtons, in the other case I get 40 newtons. Now which of those is the best way to rip the rope in half? Tree. Right. The tree, right? I want to get as much force as possible. So 40 newtons is the right answer. That's B in case you didn't hear me. All right, I'm going to stop at 220. 220. That's a lot better. All right, just a couple more questions. All right, anti-lock brakes keep the car wheels from locking and skidding during a stop. They're actually pretty interesting, anti-lock braking systems in cars. You know, you might have an old car, like pre-80s. Yeah, so like we had a bunch of old cars. My dad and brothers were both mechanics. We had a bunch of old cars. And what do you have to do if you're out on the wet road and you want to stop? You're in your old 64 Ford truck or whatever. What do you have to do to the brakes? Yeah, you have to tap them. You don't slam on them if you want to come to a quick stop. You tap them and then you sort of pump the brakes until you come to a stop. Well, in modern cars, they do that automatically. So whenever you slam on the brakes because you want to stop really quickly, in your rotor, you have those brake pads that clamp down onto the rotor to make your wheel stop turning. They do it really quickly. Like they'll cycle on and off so that it doesn't cause your wheels to lock up. Now, when you have car wheels that are spinning on the road, so if this is the road and I have a wheel that's spinning along the road,
what is the type of friction that is at play there? Is the friction static friction or is it kinetic friction? When you have a wheel that's spinning along the road. You think it'd be kinetic, right? But it's not, right? Because you want to think about the surfaces of the tire. The surface of the tire and the surface of the road. When the wheel is spinning, I'm going to show you a video in a second here. When the wheel is spinning, the surface of the tire and the surface of the road are stationary with respect to one another. Now the wheel spins, right, and that's what makes the car go forward. But when the wheel locks up, what happens to the surface of the tire and the road? It slides like that. And that's what type of friction? That's kinetic friction. So your anti-lock braking system, what it does is it keeps your wheels spinning but slowing down so that your static friction is always at play. So that's what an anti-lock braking system does. But why does this help to slow the car down? Can you describe it in terms of your coefficient? Remember this mu symbol is the coefficient of kinetic or static friction. Is the coefficient bigger than the static friction or smaller? Is the coefficient of kinetic friction bigger or smaller than the coefficient of static friction? Which is better, the sliding or the kinetic friction or the static friction? Okay, I'm going to stop at 310. 310. Just guess if you don't know. Remember, on these questions, you get credit if you get the wrong answer, but you get twice credit if you get the correct answer. All right, let's see here. So my static friction is bigger than my kinetic friction, and static friction is better. So you want to keep that static friction for your wheels. So D here is the right answer. Static friction almost always is bigger than kinetic friction. That's why when you're pushing an object, it's difficult to get it moving. That's why when you have your car wheels spinning, you want to keep them spinning. You never want them to lock up. So that's why you pump your brakes. Or you don't pump your brakes in modern cars, but in old cars, you pump your brakes.
Is there a situation where kinetic is better?
I think in just some very few materials, your kinetic friction can be bigger. I don't know of any right offhand, but I think it can exist. I can't think of it. All right, one more here. We've talked about this, but your little sister wants you to give her a ride on her sled. On level ground, what is the easiest way to accomplish this? Do you push down in the front, or do you pull up in the back? Excuse me. Do you push from behind, like this guy, where he's pushing down, or do you pull up from the front? Both are equivalent. It's possible. I told her, get out and walk. I'm pulling that man's sled. E isn't the right answer, by the way. Which of these is the right answer? What's the easiest way to accomplish this? We talked about this a day or two ago. We're doing pretty well. Another 10 seconds, I'll stop. Excellent. B is the right answer. You want to pull from the front because you remember our friction is dependent not only on the coefficient, but it's also dependent on what? The what type of force? Everybody says all at once, not all together. What did you say? Okay, no, that's not exactly right. Thank you. No, not the weight. It's related to the weight, but really
friction, now you need to notice when you think friction is dependent on the coefficient of friction, static, kinetic, and some force. What is that? No, not the gravitational force. The normal force, right. So remember I have the ruler, and if I hold it down, it's really hard to pull because I increase the friction by increasing the normal force. The same is true here. That if I pull like this, I decrease the normal force, so I decrease the friction. So if I push like this, by pushing down on the desk, even though I'm pushing at an angle, I'm increasing the normal force. And so, I think, you have to try this and see how it goes, is that when you go to the grocery store, how do you push the cart in the grocery store? Like this, right? That's how everybody does it. They push the cart like this. But I think instead, everybody should do this. Because then we have less friction on the cart. So next time you go to the grocery store, instead of pushing your cart like everybody else tells you should do, I want all of y'all to try it like this. And then, that'll decrease the amount of friction, and it should make life a lot easier for you.
Your heels get caught.
So don't wear heels.
No, like,
Oh.
your high heels, just
Oh,
like, it like sneaks it like, it's
You've tried it? Oh, have you? I haven't tried it. Okay, but the rest of y'all try it. Okay. I'll watch a little video about friction. It's not really a video. I like to cycle, and so this was from the Olympics, the triathlon. It was the women's triathlon, which is amazing. Like, just the way they do this is really cool. But at one point in the bike section, there was some oil or something on the road, and so there was a lot of crashes. And so this is like a crash reel from the women's triathlon. But I want you to think about what is the type of friction that's at play, and is it kinetic or is it static? Because when you're riding a bike, there are actually instances where you have both static friction at work and kinetic friction at work. Ideally, you'll always have static friction, but in this case, you start to get some kinetic friction as the tire starts sliding across the road. So let's just watch this. It's just kind of fun. Well, I'm sure it wasn't that. And then, like right after that, I didn't record that, but they start talking about the benefits of static versus kinetic friction. Gosh, they really need some better static friction. Because when their wheels start sliding, that kinetic friction takes over. And kinetic friction, once it takes over, man, you're done, because it's really a lot smaller than our static friction. All right? So if you ever crash on your bike, likely it's because kinetic friction came into play and not static friction. You don't want your wheels to slide. Okay, let's see. Any questions about Newton's laws? I'm going to post these concept tests that we've done and the previous one that we did as well on unit dimensional analysis and stuff. That would be a good way for you to study for the test. Sometimes, often actually, I shall just pull some questions straight from those concept tests. And then there'll be other questions, there'll be variations of them. All right, but it'll be a good way for you to study for the test, besides reading a book and what have you. Okay? All right, let's talk about torques. Excuse me, not torque. Torque. You probably know what torque is. What do you think of when you think of torque? What do you think of? Like a rotational motion, things spinning. Run?
Something like that, right?
Right, yeah, so I always think of like a torque wrench, right? And a torque wrench, you apply a certain force at a certain distance from whatever you're turning, and then applies a certain torque. Does anybody know what the units are on a torque wrench? Foot pounds, right. So foot is our unit of distance, and pounds is our unit of weight. So we're going to measuring torques as a force times the distance, our Newton meters. So we'll be looking at torques in Newton meters. So if we think of forces causing an acceleration, which is true by Newton's second law, we can think of torques cause acceleration in a circle.
They cause things as Caitlin? Yeah, as you said, rotary? Yeah, they cause things to rotate. So torques cause rotation. Though when we deal with torques, we'll deal largely with static situations. We'll look at several examples where muscles cause joints to move, but we'll look at them in a static situation. How much force is required to keep your body in place? But first, just mathematically, we define torques. It's the Greek letter tau, and it's equal to the force times the moment arm. And in particular, I'm looking for the force that is perpendicular to the moment arm. Let me draw you a picture. Let's say that I have some object that rotates about this point. It could be whatever. We'll look at the bones in this scenario. But I have some object that rotates around this point. If I apply a force to it in this direction, that'll cause a torque. Whatever force I apply to this moment, this is called the moment arm, the meter stick is called the moment arm. Whatever force I apply is the force that goes here. And then the distance from where I apply the force to the axis of rotation is that value r. So if I apply my force here, that's my force. And then this is the distance r. Now, this force has to be perpendicular. If you have a force that's not perpendicular, like let's say, for example, I'm pulling sort of in this direction, then only one component of my force is going to cause a torque. And if you think of the extreme of this, where I'm applying a force that's not perpendicular at all, but instead along the moment arm, so let's say, for example, I apply a force here, what will be the torque caused by that force? Or will it cause a torque? No, this will cause no torque at all, because that force is not perpendicular to the moment arm, but is parallel. Right? So when you open the door, for example, whenever you open the door, you always push with a force that's perpendicular to the door. Right? You don't ever, however, not all of you are going to be able to see this, but you don't, however, push with a force that's parallel to the door. You follow what I mean? Like if this is the door, I don't come and try to open it by pushing on the end of the door. Because then you'd look kind of stupid, right, if you tried to do that, because you wouldn't actually open the door at all. Further, if I want to open the door, I always push as far away from the moment arm as possible, because that increases which of these values, F or R? It increases R, which is the length of my moment arm, which is the distance from where I apply the force to where the axis of rotation is. However, if I try to open the door here, I can do it. It's just going to require a greater force because my moment arm is shorter. We're going to work through some simple problems in just a minute where you can figure out what is that force. All right, so let me put some of that in words. This is called the moment arm. It is the distance from where the force is applied to the axis of rotation. Right? This is the axis of rotation in this case. It's just that point where your object rotates. And our force, the component of the force that's perpendicular to the moment arm, is that which causes the torque. I'm going to draw another picture to explain that in just a second. So the component of the force perpendicular to R, that's the moment arm, causes the torque. We don't get much into vectors in 2 dimensions, but I do want to sort of take just a moment to talk about this. when you have a vector, say a force vector, I'll draw another momenton down here. Let's say this is my axis of rotation, and now I have a force vector. I'm going to say that is applied like that. So that's my force vector. I can think of this vector, this force, being in two different directions. I can think of it being in the x direction and the y direction. So I can break it up into two separate components. I can break it into its y component. That's the part of the force that's acting in the y direction. And I can break it into the x component. Only one of these components is actually going to cause the object to rotate. Which component of that force will cause it to rotate? Fy or Fx? What do y'all think? All right, let's imagine. So this is my thing. Let's see. Noel, can you hold this? You do the axis of rotation. Just hold it like that. You're a good axis of rotation. That's good. So there we go. All right, now if I pull on this, this will represent my Fy. Right? I pull it up, look, it causes it to rotate. Fx would be like if I pull down like this. Am I causing it to rotate if I pull in the x direction? No. So which component of the force causes it to rotate? Fy. So that's the component that is perpendicular, that's what this little symbol means, is perpendicular to the momenton. So Fy here is the only part of the force that causes rotation. All right? Which is why when we're trying to open a door, we don't push on it like this from the end, because that doesn't do anything to the door. It doesn't cause it to rotate at all. Okay. One more thing. When the object is not rotating, the net torque equals 0. This is just like when we said objects don't accelerate, the net force is equal to 0. When objects are not rotating, the net torque is equal to 0. Let's look at it. And we generally take this, it's not terribly important for y'all for reasons I'll show you in just a bit, but generally a torque in the clockwise direction is considered to be negative, and the counterclockwise direction is considered to be positive. That's not terribly important. I'll show you why. Because the problems, it doesn't really matter what sign you attribute to the direction. It's just that one torque in one direction, if you call it positive, then you'll call the torque in the other direction negative. Let me work through a problem. Like, let's say that we have a seesaw. Right? And, you know, my kids like to seesaw. I have a 6-year-old little girl. I'll put her down here. She's probably, well, she's about 45 pounds. A pound is, or a kilogram is how many pounds? Does anybody know? How many is it? Well, let's just say 2. All right, so we'll just sort of round that off to 2. A kilogram is 2 pounds, so that means that she's what? If she's 40 pounds, she's how many kilograms? 20 kilograms, right? Yeah, so she's about 20 kilograms. Right? And I'm about 70 kilograms or so. So where am I going to go on this seesaw if we want to balance it? Y'all ever been on a seesaw with a kid? Where do I go? Do I go here or do I go closer in? I have to go closer in. So if I have a mass of 70 kilograms, let's say that this distance is 1 meter, then I want to know what is this distance. I'll call this x. I know that this situation is going to be in equilibrium. It's not rotating. That means that my net torque is equal to 0. So if I were to sum up the two torques, they would equal to 0. So the torque, you get Ada, that's my daughter's name, minus the torque due to me would equal to 0. And then I want to solve what is that torque. I have a force that's acting downward for eta, and then I have a force that's acting downward for me. For eta, that's going to be 20 kilograms times the acceleration due to gravity, which is 200 newtons. Remember, F is equal to m times g, and g is equal to 10. That's an acceleration. And for me, the force is 700 newtons. All right? So I would say 200 newtons, just the force where eta is, times 1 meter, minus 700 newtons times this distance, x, will equal to 0. And then I can solve for where I need to be. And let's see, that turns out to be x is 200 over 7 over 700, or 2 over 7. So we'll just leave it as a fraction, 2/7 of a meter, under half a meter.
You could see a problem like this where you have to find what is the force required to balance a rotating system, or what is the length of the moment arm. It's going to be such that you won't need a calculator. So let's do one that's similar to what you might see on a test. Can I go down from here?
Right, so I'm just going to write it. You'll need your clicker. Let's say that we have a situation like this. I have a moment arm. Let's say that I have a force of 2 newtons. It's acting at 1 meter from the moment arm. And then I have another force here. I don't know what it is. I want to know what it is. And it's acting at 2 meters from the axis of rotation. And I just want to know what F is. Is F 2 newtons, 4 newtons, a half a newton, or 8 newtons? What is the force required to make this so that the sum of the torques equals 0, so that it doesn't rotate? For this to be an equilibrium, for it not to move. Would that be 2 newtons, 4 newtons, a half newton, or 8 newtons? Oh, I'm sorry. Huh? It's supposed to be 1, right? Let me give y'all some other answers. Just everybody put A. Everybody put A. Let me give you some new numbers. Sorry about that. Everybody got A in? Alright, I'm gonna stop it. Alright, let's say this is 4 newtons. All right. What is the force required, F, to make it balance, to make it so that the equilibrium, so it's in equilibrium? All right, I'm going to stop at 50 seconds. You can ask your neighbor what they put. I'll stop at 1 minute. 1 minute. Most of you have it right now. 1 minute, I'm stopping in 5 seconds. Okay, that's pretty good. Did y'all hear about oxygen and magnesium? They started going out together. Y'all hear about that? Y'all hear about it? You didn't hear about that? When I heard about it, man, all I could say was OMG. A 9-year-old told me that one. That's pretty good, right? All right, let's see. So, what y'all put? Did I already mark it right? Well, okay, what did I mark? Where is it? Oh, I see. I got you. Thank you. All right, yeah, so A is the right answer. So I just say the sum of the torques is equal to 0. The torques due to this one is going to be 4 newtons times 1 meter. And then the torques due to this force will be minus some force times 2 meters, and then that'll equal 0. So if I solve now for F, I get a negative 4 over negative 2, which is equal to 2 newtons. You probably don't have to go through that algebra. Most of you got that right. You should be able to just sort of look at it and tell what is the answer. But you want the torques to be the same in both scenarios. Or another way that you might want to write this is that you would write 4 newtons times 1 meter is equal to some force that I don't know what it is times 2 meters. I know that those torques in different directions have to be equal. In order for this to be the case, F has to equal to 2 newtons. All right, you'll see a simple levers problem like that. Levers are pretty important in the human body. We're going to talk about the different classes of levers, and then we'll see how they're in, like how those different classes of levers are used in the body. Y'all okay with this? Yeah, okay. Well, let's look at the 3 classes of levers. These are discussed in your book. You will need to be able to identify what those 3 classes of levers are and where in the body they're used. So like I'll provide you with a diagram and ask you what class of lever is this. I'll provide you with a picture of the foot or the arm or whatever and ask you what type of lever is this. So we have 3 classes. The class 1 lever, there's a picture in your book by the way, looks like this. I have a fulcrum, that's my axis of rotation. I have some load, and then my effort is down here. My class 2 lever, my fulcrum is at the end, my load is right here, and my effort is right here. And then my class 3 lever looks like this. There's my fulcrum. My effort here is here. So that's the force that you're applying. And then your load is here. All right, so those are our 3 classes of levers. You can have your effort and load on opposite sides, like here. Your effort and load on the same side from the axis of rotation or from the fulcrum, or then you can switch them in either way. So class 1 is when they're on opposite sides. This generally gives you the easiest means of moving something. And then class 2 and 3, the load and effort are both on the same side. Class 2, the load is in the middle. Class 3, the effort's in the middle. Let's look at some pictures of the human body, and actually no, we'll come back to that in just a bit. We'll come back to this after we get into the levers in the human body. Well, let's look now at some stuff about the human body. Can I go down from here?
You said the fulcrum is the axis of rotation.
Right, yeah, so this is the axis of rotation. It's also called the fulcrum, or the axis of rotation. All right. So typically when we go through these chapters, I'll do sort of the physics portion first, just like in your book, and then we'll cover the biology section, the anatomy section after that, and we'll start to talk about like how are levers used in the body and what have you. So I won't cover all the information, but I'm just going to sort of hit the highlights, and on your test you'll have the highlights. On the reading quiz, everything's fair game. Y'all aware of this? Understand? Okay. So you have 3 types of muscles. you have skeletal muscles. These connect to the skeleton and they're used for large external motions. We have the cardiac muscle. We'll talk about the heart and how it works in a later chapter. I think in the next chapter, actually, when we get into fluids and how fluids and pressure and what have you. So the cardiac muscle is the heart. And what's the last one? The third one? Smooth, right. Smooth type of muscle, is used to move fluids in the body. We've already talked about this a little bit. I think I gave a question about it when we were sort of practicing for the quiz. But when you have muscles that are attached to bones, we call those a couple different things. So the points where they attach to bones are the insertion point and the origin. The origin. One of these moves and one of these doesn't move. Which one is it? Right, the insertion point moves, and the origin, that's like where the force originates, I guess, is the one that doesn't move. So the insertion point is the end that causes the bone to move. So the end of the muscle that causes the bone to move. And the origin is the end that is stationary, or the end that doesn't move. Right, so for example, your bicep, I guess, is connected right about here, and it causes your forearm to move back and forth. Where it's connected here is called the what? This is your insertion point. It causes your forearm to move back and forth. And where it's connected up here, I guess, roughly, this is called the what? That's the origin, all right? So be able to know what those are, be able to define them, and be able to identify them, like if I give you a diagram or whatever. By the way, my wife, she teaches the astronomy class. Anybody ever taken that? Do you know my wife works here? Do you know that? Yeah, we're in the same department. But on her first day, I got her this new dress for our anniversary, and it was a really cool dress. And she thought, oh, I could wear some tights with this. And she got some of those like printed tights from Amazon that had like a star forming region on it. They're really bright and colorful. It's not really like her thing, but she got it for class. And so she wore it the first day of class. Y'all know what I'm talking about? Ladies, y'all seen those? I've seen women over in the rec center that got them. But they're tights, but they're printed with like all star forming regions and astronomy things on them. So when I was looking at them, I saw online that you could also buy tights that had like all the muscles. Have you seen that? And I told her I was going to get some and wear them. But then she said, no, you don't want to do that. Like, it's different. A guy should do that. Right? I wasn't really serious. I'm not going to wear muscle tights to class. But if y'all want to do that, that's fine. Guys, it's okay to, like, no, don't wear muscle tights. All right, let's see. Joints. So those are the places where muscles attach to the bones. With joints, we have several different types of joints. This is where two or more bones meet. The synovial joint. This allows for large movements. Y'all probably know more about this than I do. What are some synovial joints? What, for example, is a synovial joint? Okay, yeah, so your elbow, which provides for large movements, thank you. Your shoulder, that's a big movement. Your knee, right, is a synovial joint. What else? Your hip. Did I miss one? Ankle. Is your neck a synovial joint? No. Okay, yeah, so these include things like your elbow, hip, ankle. Are you sure ankle is a synovial joint? Pretty sure. I don't know. I'm asking you. I don't know. Huh? Okay. All right. Knee. These provide for these large movements. Cartilage covers the end of the bones. And there's a cavity where synovial fluid, or with synovial fluid for lubrication. I have a picture I'll show you in just a second. Y'all all had this stuff before? Is that right? Yes? Anybody get new to people? This information? New to anybody? It's okay if it is. The book goes into it in more detail, but for the test, I want you to be able to identify these things. I'll show you some pictures. You might have to identify them from a diagram. So you have a picture of the synovial joint somewhere. There we go. So this is, I think this is from your knee, actually. Is that right? Anyway, it's some joint. But there's a cavity here where you have this fluid in between the bones. They're covered with cartilage, and then you have this fluid that causes for lubrication. I understand that as you get older, that fluid can go away, correct? Is there any way to get it back? Injections? Really? Really? Okay. All right, let's look at the application of muscle tension. This is where we'll talk about isotonic and isometric. As we talked about, like with the rope, when you have the rope attached to the tree, the same is true for the muscle, that the tension force is felt all throughout the muscle. If I have a force of, 100 pounds or whatever at the insertion point, that 100 pounds is felt all throughout that muscle, from the point of origin to the point to the insertion point. I can have two different types of contractions, isotonic and isometric. This causes motion. And isometric does not cause motion. All right, so if I'm lifting something, I lift this book. This is an isotonic contraction of the bicep or an isometric contraction? This is isotonic. But if it's really heavy, I can't lift it. I can just sort of hold it right here, but I have to apply tension in order to hold it. That's called what? Isometric. Right? All right. Let's look at the types of movement, and then I'll hand back your your quizzes from last time. Although, can I tell you a story? This was kind of funny. I didn't really know what to do with this. I told you I started lifting weights a few months ago because of various injuries, and it sort of helped me to recover from some of them. But the other day I was in the gym, and one of my students comes up to me, and I was on like the leg press or whatever, and he's like, "Dr. Young, I don't think that you're lifting enough weight on that." And I said, "Well, it is what it is." And actually, I have some knee issues, so it wasn't pretty lightweight. But and then he started looking at me. He's like, "That's not very much to lift." I'm like, "Well, it is what it is." It's like, "You're a lot smaller than I thought you were." And he said, I have much stronger legs than you." And he just sort of kept going on and on. He was nice about it. He was just sort of, don't do that, please, if you see me over in the gym. All right, let's see. All right, so we have types of movement. We can have gliding, angular, and rotation. Gliding is when you have two flat bone surfaces that move with respect to one another. They glide across one another. What's an example of the gliding joints? In your wrist and in your feet and your ankle, right? You have these bones that glide across one another. So wrist and ankle. That's an and. You have angular joints, or angular movement. The angle between the movable and the immovable bones change. So a good example of that is what? In your what? Right in your elbow, right. So my immovable, my movable, it's this angle. It can be 90 degrees, it can be 180, it can change back and forth. So that's an angular movement. And then rotation, things like your head, for example, the bone twists on its long axis. On its long axis. All right. I want to do one more thing. So before I hand that back, I want to. We're going to identify some levers in the body. Remember our 3 classes of levers. I'll pull it back up again, but these are 3 levers that are in the human body. There's your foot with the fulcrum. Sorry. There's our foot with our fulcrum. At the base of the foot, the weight is the weight of your body that's pulling down, and then the effort that you require is up. So your effort is from your calves that's pulling up. This is your head. Our fulcrum is right here. This would be like nodding back and forth. The weight of the head pulls down in this direction, and then this is our effort, the force required to hold it. And then this is another lever where our axis of rotation, our fulcrum is here, our effort is right here, and then our weight is right here. What are these 3 classes? What is the first class? That's a second class lever, right? That's a second class. Right, so on a second class, the effort and the load are on the same side.
across from the fulcrum. And in this case, the load for the second class is in between the fulcrum and the effort. What kind of lever is this? Now this is one where our fulcrum is in the middle. What class is this? This is our first class lever. And that leaves the last one as a what? The last one is a third class lever. So you can see an example of that, like one is our joints in our body and asking you what type of lever is that. We'll also work through some problems next time where we have to actually calculate what is the force required to move it by looking at our torques. This is from your book, by the way, this figure, so you can find it there. All right, I'm going to hand back your quiz. Your quizzes, the way that I grade them, there's no grade written on it, so your grade is on Moodle. All right, I'm going to write the correct answers up on the board right now, and you can, if you want to just, probably a good idea for you to know the right answers, you can use it to study for the test. I often pull some questions from this for the exam, so you'll see at least a couple of these questions again. So I'm going to write the answers here. E, C, probably next time we'll move into chapter 2. And the exam, which is in a few weeks, will probably cover chapters 2. And hopefully a little bit of 3. I don't know what chapter 3 is about. I don't see it right off. Chapter 2 is pretty long. It might just cover chapters 1 and 2, but we might get into chapter 3 as well. All right, so when I hand this out, you can go, although I would do a quick grading of your exam, just so that you know what the right answers are. Brianna? Okay, if you want to just come up to the front and get it. Josh? Jason? Luana? Corey? Chanel? Eileen? Caitlin? Okay. Jason's not here, right? Alyssa's not here? Alyssa? Oh yeah, Alyssa. And Alicia as well. Alicia, Noel, Kristen, Ellis, Olivia, Trin, Brent, Lucille, Noel, Ellis. Brent's not here, right? Everybody else doesn't have one. Taylor, Kaylin, Patrick, Tate, Michael, Mike, Ron, Louis. Taylor? Patrick? You can go when you get your... Okay. Guys, hang on to those quizzes, okay? Because I will pull questions from the quiz. It's good for you to tell them.